Alright, hello everyone, this is John again, and this is now part 3 of the 3-part video series on how to calculate a one-sample t-test. The difference is with this third part, we're going to switch gears, and instead of manually calculating a one-sample t-test, which we did in the previous 2 videos, I'm going to show you how to calculate a one-sample t-test now in RStudio. So to quickly recap what we've already covered, in video 1 we did a manual calculation for a one-sample t-test completely by hand using a step-by-step process and provided example. In video 2 we continued from video 1, but this time adding some additional features that you most likely would like to include with your one-sample t-test, which included confidence intervals, effect size, and percentage variance. We used the same provided example, just added some more features. If you did not see these 2 videos and are interested in manually calculating a one-sample t-test, I would recommend watching those videos as well. So in this video, video number 3 now, we're going to switch gears and now use the same provided example, but calculate everything we did in the last 2 videos now in RStudio. So to quickly recap the question, Bill finds out that the average student at his college campus walks approximately 7.05 kilometers a day. Bill buys a pedometer and measures how much he walks over the next 7 days. Bill finds out he walks approximately 9.07 kilometers a day with a standard deviation of 2 kilometers. Using Bill's data, calculate a one-sample t-test, two-tailed, and determine if Bill walks more steps than the average student at his college campus. So we've actually answered this question, and we answered this question back in video 1, and you can see here I have the whole thing highlighted in red. The results said or suggested that we can reject the null hypothesis, as Bill is indeed walking significantly more than the average college student at his college campus. And here's our scientific notation for a one-sample t-test, and the section that we have highlighted blue here is the hand calculations we did in video 2, calculating the confidence interval, which we have here, the effect size or Cohens D, which we have here, and then the percentage of variance, which we have here. So pretty much everything that we have here now, we're just going to replicate it in RStudio, just so I could demonstrate how you might want to do these calculations within a statistical platform such as R. So let's switch over now to R. So I already have my script open, and I'll just show you step by step on how I would calculate a one-sample t-test in R. So the first thing you're going to have to do is input or upload some form of data. In the questions that we were previously using, the example question, we didn't have the raw data of how much Bill was walking every day. We just had the mean of that data. But in R, you're really going to need the raw data in order to calculate a one-sample t-test. So here I've actually provided the raw data that was not provided in the initial example. So here are each of the 7 days how much Bill was walking each day. If you ever need to input the raw data, it's quite simple. You would just put C bracket, then each of your data points separated by commas, and then close the bracket. So if I highlight this now and do a control run, I now have over here Bill's data. So we have all 7 data points on how much Bill was walking each day. Now the next step we're going to do is actually examine the distribution of Bill's data. In the initial question, both in video 1 and 2, we couldn't actually test the distribution of Bill's data because we didn't have all the raw data points. But here we do, and here we should be looking at the distribution of the data. Just in the previous questions, we had to sort of take it for granted that the Bill's, or just at least trust that Bill's data was normally distributed. So here I'm going to show you 2 methods on how you might want to proceed calculating or at least developing a histogram. The first one I'm going to use is library R companion. I'm going to control run that, and for sake of advice, if you don't have R companion, it's probably something you're going to have to install and download. Quite easy to do. You just go to tools, install packages, and then from there you should be able to actually just type in the name of the package, R companion here, and it should you should be able to install it. But anyway, let's continue. We're going to use the function plot normal histogram. This is the function you would be using, and then in brackets you would put your data, whatever your data is called. So if I control and run this, here we get on the side here a plot of the histogram. So this is Bill's data. It's based on visual inspection. It looks normally distributed. So in this case, we have nothing really to worry about on whether the data meets the assumptions or not, because it's normally distributed. So this looks pretty good. I have another method here as well that you might want to use when calculating a histogram for data. This is a bit of an alternative method, and instead of using R companion, I'm going to use library using R. So I'm going to run that package. I'm just going to clear that. And here it's quite similar to the previous one. It involves a few more steps, but the reason I'm using these steps is I'll highlight here and run. Is you could see the results are practically the same. This is just an alternative method on how you might want to run a histogram, and the reason I'm using this method here is because here under sequence, why I like this method is because I can actually suggest how long I want that line, that bell curve line that is being provided there. I could suggest how long I want it to go. I want it to go to end. As you probably noticed in the previous histogram, which I don't like, I can actually run it really quickly. You could see the line sort of has a gap here. I don't know why it does that. So sometimes I use this alternative method because I can actually state that that line should go right to 6, which it should be doing here, and then right to 12, which it already does, but it unfortunately there's that gap there, and have a length of the 7 data points. So that's why I like using this method. But you could see there's a few things you need to change. I have Bill here for histogram, and then I have the mean for Bill's data here, and then the SD, which is a standard deviation for Bill's data. Something that you can mess around with if you feel necessary, but these are just two methods that I could use. I just sometimes like this alternative method because if that line isn't going from end to end, I can at least manipulate that line here with actual numbers. So one thing that I'd like to do that we did not do in the previous 2 videos is actually test for normality. I want to test that Bill's data is indeed normally distributed. And in order to do that, you can use what is called the Shapiro test. You don't actually need any library packages to run this, but Shapiro test is going to tell you whether or not your data significantly differs from a normal distribution or not. So if you don't feel confident when visually inspecting your data, meaning if you look at this and you're not confident enough to visually say whether or not the data is or is not normally distributed, no need to fret, because you can use the Shapiro test on the data to determine whether or not it significantly differs. So if you see below here, actually I'll just leave it like that, we actually have Bill's data, and the p-value for the normal distribution is definitely not significant. It's not less than 0.05. So this is a great way for you to at least find a number on how much your data could deviate from a normal distribution. And in this case, it doesn't. So that's just an additional feature you might want to include before calculating a one sample t-test. And then of course, if you wanted some descriptives from Bill's data, it's quite simple to do. You can do mean bracket Bill, as Bill is the data, and SD bracket Bill, as SD is the standard deviation. If we run both, you could see we pretty much get the exact same results that were provided within the question. Bill's data, the mean is 9.07 with some extra values behind that. And then the SD here, it's a little bit different than what was provided in the question, but it's practically identical. It's 1.9. It's just separated by 1 decimal point. But you will see in many cases, if you're doing a manual calculation compared to a calculation in a statistical platform as R, your values are going to be practically identical, but they might slightly deviate based on the decimal point. But let's continue. So we know our mean, we know our standard deviation, we know the data does not deviate from a normal distribution, so we can actually proceed with a one sample t-test with confidence, knowing that the test would be appropriate for this type of data. So this line here is actually how to calculate a one sample t-test in RStudio. So it's just you use the function T.Test, and then in brackets Bill, as Bill is the data we are using. And this is one of the key features you need for a one sample t-test, is the mu value. The mu value is your population mean, and we knew from the question the population mean was 7.05. So that's something you need to actually include within your line of script here, is that mu equals 7.05, as that is the value we want to compare to Bill's mean, which is down here. So there's a few other things you might want to add. You don't need to add them right away, but if we're going to run the t-test, we might as well run all of it together. Number one, you need to state whether it is a one-tailed or two-tailed test. So you'd actually have to use the function here, alternative equals, and then you would state two-sided or one-sided, and because it's a two-tailed test, we're going to use two-sided. And then here's the next part, is the confidence interval, which says conf level. Here we have 0.95. So this is pretty nice, because if you run this whole line of script as follows, it is going to run Bill's data and compare it to the mu or population mean. It's going to be a two-sided test or two-tailed, and then we actually state, give us the confidence intervals, which would be at 0.95, at 95%. But if you wanted to change this to 50, 80, or 99, you could easily do it within this line of code. So let's run this now. And here are our results for Bill's one sample t-test. So the t-test is 2.77, pretty close to what we calculated in our manual calculations. Our manuals was 2.69, which would be roughly at 2.7, so practically the same. The only difference, the only reason we're seeing a slight deviation from this t-test to our manual is because the RStudio is accounting for more decimal points beyond just the 2 decimal points we used within the question. But you can see the degrees of freedom is the same at 6. If at any point your degrees of freedom in RStudio is not the same as the degrees of freedom within your manual calculations, you know you did something wrong, because this should not deviate in the slightest. But here's our exact p-value. So when we did the question manually, we knew that 2.69 was lower than a p-value of 0.05, but we didn't know really how much lower. But here we actually get the exact p-value. The exact p-value here is 0.03. So we know that's the exact p-value associated with the t-test. That's about 2.7. And here's the next part that's quite important, which is the confidence intervals. So similar to the confidence intervals that we manually calculated based on the question, here is the lower and upper limit of the confidence intervals in RStudio. They're practically the same to what we manually calculated. The only difference here is ours taking into account more decimal points than what was provided in the question, hence why the values are slightly a bit different. And then of course it gives you the sample mean of Bill's data, which is no surprise. We already knew that. So that's how you calculate a one sample t-test in RStudio. But we're just going to quickly do some last things that we also calculate in video 2. We're going to calculate the effect size, which is Cohen's D, and then we're going to calculate the percentage variance, and I'll get into this one momentarily. So with the confidence intervals, you could easily just include it within the line of script when calculating a one sample t-test, but for the effect size, you're actually going to need a separate library and calculate this completely separate from your one sample t-test. So in this case, you need to download library LSR. So I already have it downloaded, so I'm just going to return it. But once again, remember, go to Tools, Install Packages, and just write LSR and then install. So with the Cohen's D, it's quite simple to do. There's only two things you really need to take into account when running Cohen's D. You need to include Bill or your data, and then you need to include mu. So since the question asked us how much does Bill's data separate from the average college student walking on campus, the mu is 7.05. So if you include that, you're pretty much ready to run Cohen's D now. So I'll run that. And we get 1.04. Our Cohen's D based on the question was 1.01. Here it's 1.04. It's pretty much almost identical. The only difference is the question didn't provide as much data points as we are getting provided here with within our studio. So yeah, but a Cohen's D, quite simple to run. We still get a large effect size, and all you need to do is use the function Cohen's D. Use this, plug in your data, the name of your data, and then whatever cutoff or population mean you're required to compare it to. And now finally, the last thing I want to calculate and demonstrate is the percentage of variance, which is also known as R squared. So if I quickly go back to the slides, the percentage of variance was this formula where we're going to square the t values and then compare them to the degrees of freedom. So it's going to be t squared divided by t squared plus df. And this is how we get our treatment effect, something we did in video 2. So when it comes to R, though, on the other hand, there's no actual function to calculate the percentage of variance. So if you're truly interested in calculating the percentage of variance, there's no real easy way of going about this. What you're going to have to do is get the t values that were provided within your one sample t-test, the degree of freedom that was provided in that one sample t-test, and literally just replicate the formula in itself in RStudio. So you can see here I have the t value squared. That little mountain peak is the squared value, so I'm going to square it by 2 divided by the t value squared by 2 plus the degrees of freedom. And you can see I've added the brackets here just so the order of operations is not mixed up. So the good thing is with R, you can use it just like a calculator. So if I go control return, we get our percentage of variance here, which is pretty close to what we manually calculated based on the question. So yeah, that's the only issue, is that when it comes to percentage of variance, that is something you're still going to have to manually calculate. But once you get the outlay here correct, you can just change the numbers if you need to, depending on if you're doing another one sample t-test or not. So yeah, so that's pretty much the entirety of the whole series here. So video 1, we did manual calculations. Video 2 are manual calculations. And then finally video 3, I'm just demonstrating how you would put it all together within RStudio, and really how you do all these manual calculations within RStudio. Definitely saves you a bit more time, but it's a good way to know how to do both. Thank you for watching.